So go ahead when you're ready, Paul. Thank you.
Okay, thank you, Susie. Hello, everyone. I'm Paul Hu from the MagLab in Tallahassee, Florida. So today I'm going to talk about YateStar, a unique tool for lengthwise transport IC characterizations. So why do we need lengthwise IC characterizations? The demand for a coated conductor is very high at present, and there are more and more manufacturers worldwide. And the question is how to characterize and select these conductors. And one issue important to us is lengthwise uniformity, since ultra-high field magnets at MagLab have so far been made with single tapes in insulated condition, and the no insulation magnets have so far been on the test coils. So based on these demands, we have developed this tool, YateStar, that allows uniformity of vortex spinning and uniformity of local cross-section to be assessed with millimeter to centimeter precisions. So here is a top view of the reel-to-reel IC measurement system. So everything is in liquid and nitrogen bath during measurement. Current go through these two pulleys, and between the two pulleys we have two magnets to suppress the critical current. And we also have this whole probe measurement system. So it was originally designed by Yates Coulter from Los Alamos National Lab, and it was further developed in our lab by improvements to indexing, increasing length capability, and measuring speed, and addition of this whole probe array. So we have this transport current, transport measurement with IC position, field angle, and field magnitude with a resolution about 2 centimeters. And we have two channel measurement with field in two directions, normally perpendicular and parallel. And with this rotating permanent magnet, we can measure the angular IC at any interesting point. And also with this whole probe array, we have the magnetization measurement with much higher resolution and the speed. So here is a picture of the first generation YateStar. And we, over the years, we are keeping improving the system. One thing was about the measurement speed. So the transport measurement speed has been vastly improved by utilizing FPGA developed by Griffin Bradford. So previously, IV curve took 15 to 20 seconds. Now it takes only 60 milliseconds. And the measure rate can reach 30 meters per hour now with a 2 centimeter resolution, which is 12 times faster than before. And we also have built a bigger version of YateStar, which is capable of measuring 500 plus meter long tapes. So we are still modifying the hardware of this big version of YateStar to make sure it works better and smoothly, but it is in use already. So what can YateStar tell us? The first thing is the IC variation in commercial coated conductors from different manufacturers, especially for vortex spinning properties. And the second is the post-mortem analysis for tapes used in magnet coils and cables, comparing the tapes before and after tests can give us a lot of information. So today I'm going to just focus on the IC variations in commercial coated conductors. Firstly, let's have a look at a statistical analysis of tapes from one manufacturer in the last couple of years. Here is a conductor zoo for the tapes received in different years. So this is the IC versus tape position with field parallel to C direction. As you can see from here, there's an apparent improvement of the uniformity for tapes received in 2013 and 2014. But to quantitatively describe the variation of these tapes, we use relative standard deviation, which is standard deviation over the mean values of each tape. So with this index, we can plot these tapes in one figure with this relative deviation versus the order of manufacturing. So we can see for those tapes, it follows the line of decreasing IC variations. But for those tapes received after 2014, we do not see obvious improvement of uniformity. They almost fell in the same levels for this relative standard deviation. For examples, here is the points of these tapes received after 2014. But there's one good thing that the longest tape this manufacturer can deliver has reached 350 meters. So that's a great improvement compared to previous tapes. To further analysis of the IC uniformities, we can borrow some concepts from statistics like Fourier transform. And so for the following presentation, I just want to remind you that the longer length in real space corresponds to lower frequency in Fourier transform, and the area under the power spectrum is the variance of ICX. With this tool, we can categorize the features of different ICX. So IC variations are like noises in time series and can be categorized into different types. And in time series, we have this white noise, pink noise, and brown noises. And for its power spectrum in log scale, we can see they have different slopes for this power spectrum. So the types of IC variations can actually depicted by this index. We call it beta. So, for example, here is a tape received before 2014, and we use the relative variance for this Fourier transform. So what we did is we have the power spectrum first, and then we average these numbers in every log2 distance. Then we do the linear fitting and to get the beta value. In this way, we can avoid bias caused by the dense point numbers in the high frequency region. So this particular tape has a beta value close to 1.1, which is very close to the pink noise. While for the other tapes that received in 2010, 2012, the beta value varies between 0.5 to 2, which means it's very hard to predict the uniformity of these tapes. You do have to measure these tapes. Usually, smaller beta value gives smaller IC variations. For recent tapes that received in 2016 and 2018, the relative standard deviation is between 2 to 4%, and beta value are close to 1. Here is the standard deviation versus manufacturing order of different tapes. Here, I'd like to show the tapes received in 2016 and 2018, and do the Fourier transform and plot and do the fitting of part of their part spectrum. So all these tapes has a roughly slope close to 1. And the thing we have to notice is that for this tape, there's a bump in the region between 10 to 100 centimeter. And it turns out this is the feature caused by the slitting in the manufacturing. So there are also other artifacts caused by this slitting process, like the slitting macro cracks at the edges, which can be reviewed in the high frequency regions. But as a matter of fact, the peak caused by the slitting wheel in Fourier transform has become less and less obvious in recent tapes. That means there's an improvement for the slitting process. And usually when something is abnormal during the manufacturing, this beta value becomes larger than 1, which also means probable larger vortex spinning variations if we do the transport measurement. So here, taking an example, we choose this one, which has a relatively larger standard deviation. So what you can see here in the high frequency region, it's pretty much the same as other tapes. Well, when it goes to the low frequency region, which means corresponding to a longer length scale, it starts to deviate from the slope 1. So correspondingly, this is the lengthwise IC of this tape. So here we also have transport data on the 2 ends of this tape. So the reconstructed IC was according to the measurement of Hall probes arrays and scaled to transport data with field parallel to C. What you can see here is there's very little correlation between ICX with field parallel to C and field parallel to AB. And the ratio of these 2 ICs with field in two directions are not the same in the 2 ends, meaning a possible vortex spinning inside this tape, vortex spinning variation inside this tape. So secondly, let's have a look at tapes from different manufacturers. For most tapes from different manufacturers, they have a relative standard deviation between 2 to 4%. Here is an example of a tape, of a 100-meter tape. So we see this is a transport measurement done by FPGA and measured at a speed of 30 meters per hour. So we saw there's a defect in this tape, but generally this is a pretty uniform tape with field into orientation, 2 directions. So if we plot the, if we count the IC in every 2 centimeter, we will have this distribution of the ICs. So it's very close to a Gaussian distribution, and it has about 2% relative standard deviation. The other thing we have to notice that the IC values with field in 2 directions are almost the same for this tape, suggesting that there's probably artificial pin centers in this particular tape, and and in fact, more and more manufacturers are choosing to use artificial pin centers to improve the in-field performance of their connectors. So proper characterization are needed to understand if they can maintain the uniformity along the length. So there are indeed vortex spinning variations in some tapes we received. So for example, this is a tape measured with field in 2 directions, and apparently we can see the several anomalies in this tape if we enlarge them. So we cut this particular region for a TM examination, and we found out that the diameter in these regions, the diameter of busy rods in these regions reached 30 nanometers, which is about 3 times thicker than the normal ones. And that's the reason caused this anomaly. And you can never see this with a Hall probe. And so to check the influence of this anomaly in liquid helium temperature, we also cut out a section from here for liquid helium measurement. So it turns out that the abnormal regions has about 10% lower IC when field is parallel to C, and it's about the same 10% lower in field angle at 30 degree, and it has about 20% difference when field is in 50 degree, and we did not measure field parallel to AB because it's too high to measure. There are also some other manufacturers do not have APCs and may have different priorities than uniformity. So here is a tape without any APCs, but the IC at 77 Kelvin 0.6 Tesla is relatively high. If we do the same thing to check the IC distribution, we see that the ICs has a longer tail in the lower IC side for tape 1, and for tape 2, it becomes more symmetric, but the relative standard deviation is large. It's about 7%. So if we take the same method for analysis, we use power spectrum for all those tapes. Beta equal 1 still holds for most of the manufacturers. So here is a summary for tapes from different manufacturers. So you can see here in the low frequency regime, most of the manufacturers are about the same level. And it seems like in the middle range, manufacturers C and D are doing better than others. And there are also so tapes from different manufacturers do have different features in their power spectrum, and we have also a manufacturer has a obvious deviation from this standard. So for now, we attribute the deviation from beta equal 1 to those artifacts like slitting. So here is a map for checking the variance distribution in the frequency domain. So we see that manufacturer F has a general larger variance than other manufacturers, and the variance in between 10 to 100 centimeters probably related to the slitting process. And here I would like to point out for this particular manufacturer B, they have developed laser slitting. I mean, it is in developing. So this peak that caused by mechanical slitting can be obviously suppressed by laser slit. And here for those variance in the high frequency regime, this is probably related to the macro cracks that generated during the slitting process. So in summary, the coated conductors are far from perfect as far as we understand, and it's very strongly manufacturer to manufacturer. But the question is how and so what? So to answer it, we needed to use YateStar. So YateStar is a tool that we have built to answer these questions. So by applying field in two directions, it allows the strong vortex spinning to be laid bare with 2 centimeter resolution. And the whole probability provides tape star functionality that all connected manufacturers use to show up scratches, local defects, and other connectivity fluctuations using a remnant field or penetration field induced current with millimeter resolution. And in YateStar, we have FPGA for transport IC measurement. So the speed can reach 30 meters per hour now, and making it very useful scan tool for production lots before magnet building. And also, as uniformity of tapes appears to have reached an asymptote for one manufacturer, and this asymptote has a broad window. And the power spectra of IC fluctuation have distinct characteristics that we are just beginning to explore. We believe that slitting damage on one or both edges is one source for IC fluctuation, but so too are fluctuations of nanorods, nucleation, and growth. The mechanical slitting gives periodic IC variations and small IC dropouts in short length scale. Laser slitting may improve the uniformity, but is not good enough yet, as far as we know. And there are intrinsic IC variations arising from the deposition process, which may be difficult to improve if the highest vortex spinning is desired. This demands great control of the APC nucleation growth, with bad consequences for local JC where the growth goes wrong. Especially for the insulated single strand magnet, fluctuations of IC due either to connectivity or vortex spinning are of concern and need to be understood. That's all I have. Thank you.
Thank you very much, Paul. That's very interesting.